Good morning, everyone, and happy Monday, if you're watching this on Monday, or happy whatever day you happen to be watching this video. Sorry I couldn't be there today, but I'm still going to tell you what I know about ideal and real gases, and we'll do some example problems, all coming from Chapter 5. A few announcements before we get started. First of all of these slides that I'm going to go through in the videos are online. So under Lecture 35, you can see them, and they're going to go in the order that I do the video, so you can follow along there if you'd like. Also, the videos are going to have most of the material that's in Chapter 5, so if you're in the afternoon class, the 4 p.m. class, some of this is going to be review. So this first video is just going to have announcements and a little bit of review for both classes, and then you can look at the topics of each video as they go on to find the ones that cover material you haven't seen yet in class. So don't forget that by tonight at 10 p.m., so Monday 10 p.m., you need to turn in that week 13 pre-quiz. Also, if you missed class on Friday of last week, I handed out a worksheet that goes along with homework 13. So it's all about gas laws, and that's going to be due this coming Friday, the 14th. There's a copy of this posted on Blackboard, and I have extra copies as well that you can get from me during class on Wednesday, or you can print them for yourself to work on. There will also be a few extra homework 13 problems on mastering chemistry, so that will be posted as soon as I am well enough to get caught up with all of this. And it'll be on ideal gases, real gases, and stoichiometry, which is the topic of this week's lab. So experiment 7 this week is gravimetric stoichiometry, and there is a pre-lab assignment. There are problems to work through and a short reading assignment. Make sure that you do those before you go to lab. We haven't talked about stoichiometry in a while in class, and not at all in depth, and so there's a little bit of background that you should review and make sure that you have figured out before you go to do the lab so you can be successful in lab. You're going to get to pick your own reaction and investigate the mass relationships there to confirm a balanced chemical equation. Okay, so let's get started. All of this material comes from Chapter 5. You should try to get through Chapter 5, do the reading, and make sure that you can work through that worksheet, preferably before you come to class on Wednesday, because we're going to go ahead and move on after Wednesday to Chapter 4, all about stoichiometry. So if you have any lingering questions about gas laws, make sure that you have them jotted down and that you ask them before we move on. So just a quick review of what we mean when we talk about gases. First of all, gases are substances that always mix thoroughly, meaning if you have a mixture of different gases, helium, nitrogen, oxygen, for example, sulfur, hexafluoride, all of those gases are going to mix homogeneously with each other. They don't segregate into different regions the way that liquids might do, and that's because there's little interaction between gas particles. There's not a difference from one gas to the next in the way that they mix because they're so far apart, the intermolecular forces don't play a strong role between them. Intermolecular forces only work at very short distances, and these gas molecules are really far apart. Also, because the molecules are so far apart, gases are very compressible, meaning you could put them in a container of any size or shape. They're going to fill that container, and you could expand or shrink that container, and the substance is going to remain a gas over the most pressures and temperatures that are close to sort of normal conditions. This all has to do with the fact that the volume of the particles is so tiny compared to the space between them. So in gases, you'd have maybe like one particle here, and then you'd go a very, very, very far distance before you'd run into another particle. So the volume of the particles themselves is very small to the volume, very small compared to the volume that the gases actually take up. Whereas in liquids and solids, we saw that the particles are very close together, right? They're pretty much touching each other, and so they've only got about 30% empty space, which is sort of the space in here, the space between the molecules as they touch. Another thing that this means about gases is that they have a density that's determined by the pressure and temperature that they're at. So the density of a liquid or a solid is a fairly well-defined property. It doesn't vary over a very large range as you change pressure and temperature. Whereas with gases, as you change the pressure and temperature, you change the density. And we'll see today how we can calculate what the density of a gas is. And of course, density is how many gas molecules there are per unit volume. So there's something at one density, and if we shrunk that volume down and had the same number of particles, there's 1, 2, 3, 4, 5, 6, 7 particles. 1, 2, 3, 4, 5, 6, 7 particles. Of course, this would have a higher density, this smaller box, than the bigger box. But they would both be gases over a pretty large pressure and temperature range. We'll see that the laws governing gases, the equations that we use to describe them, are based on observations that scientists made over the years. But as a result of those observations, they were able to piece together how the molecules in a gas must be behaving in order for it to follow the macroscopic behaviors or the laws that govern it. And the theory behind this at the microscopic level is called the kinetic molecular theory of gases, or we'll just call it the ideal gas theory. And it's a theory because it's describing the underlying principles that give rise to the laws or equations that we're going to use. So 3 very simple points in the ideal gas theory. The first being that gases are point particles, meaning they have no volume themselves, that it's mostly empty space in a gas. And in fact, if it's a perfectly ideal gas, that means that the particles themselves, the gas molecules, have absolutely zero volume. Of course, this isn't true for real gases, but if the gas molecules are sufficiently far apart, it's a pretty good approximation. Probably the most important part of dealing with ideal gases is this point 2, that when we're talking about an ideal gas, we're looking at the molecules as being little hard spheres, little billiard balls, moving in completely straight lines, having elastic collisions. That means the kinetic energy of the particles before they collide and after is conserved, so none of it can be converted to potential energy for something to be a perfectly ideal gas. Well, what does that mean? That means if you have molecule 1 coming and interacting with molecule 2, now my gas molecules are really big, when they bounce off each other, the total kinetic energy stays the same. They don't stick together at all. That stickiness between molecules is potential energy. It's the energy of essentially a chemical bond. And so the ideal gas theory says, okay, if something is a perfectly ideal gas, they don't interact at all. So they collide without sticking together, which is to say there's no attraction between particles or repulsion. And this also has the implication that as they move past each other, they don't feel each other. So moving in straight lines means that if this molecule A over here were to pass by some molecule B down here, it doesn't feel it, even if they pass very close to each other. Of course, if they were attracted, that trajectory would be a little bit different because it would maybe move closer to the particle as it goes by it, or if they were repelling each other, of course it could be pushed away from it. But according to the ideal gas theory, that doesn't happen. The particles don't feel each other at all. So this guy just goes in a straight line, and this guy goes in a straight line, and they go on their merry way without ever feeling each other. And the last point in ideal gas theory, or the kinetic molecular theory of gases, is one that we're going to use a lot today. And it just says that the temperature tells us the average kinetic energy of the particles in a gas. So temperature is a measure of randomized kinetic energy, and it doesn't matter what the gas molecules are. If they have the same temperature, then they have the same average kinetic energy. So before we move on, take a stab at this question. So why does any combination of gases form a homogeneous mixture while mixtures of liquids often separate? Be careful to give the best possible answer from the choices that are given that answers all parts of the question. You may pause the video, take a moment to think about this, and then we'll discuss the answer. Okay, so why does a combination of gases form a homogeneous mixture, but liquids often separate? Well, choice A says gases are mostly empty space. That is true, and that would answer the first part of the question. Why does a combination of gases form a homogeneous mixture? They're so far apart, it's mostly empty space, so the intermolecular forces only act at short distances, and they're not really going to be able to act on these gas molecules that are so far apart. But that doesn't really answer the second part of the question, which is while mixtures of liquids often separate. And so B would be a better answer because it talks about intermolecular forces in liquids as well. So liquids feel stronger net intermolecular forces because their particles are closer together. And that means if you have liquids with two different identities, they're going to have different intermolecular forces felt between their particles. And so then if you try to mix them together, so let's put our little blue molecules next to our little red molecules. Now there's an entirely different force felt between these two. It's not true that liquid molecules are going to repel each other. So if the red were oil and the blue were water molecules, they're not going to mix thoroughly. They're going to separate into different regions, but recall that that's not because they're repelling each other. There is still an interaction between these two. But down here we have hydrogen bonding in the water. In the oil, we have only dispersion forces. Since the hydrogen bonding is so strong, it's not going to break apart to form dispersion forces with oil molecules. So liquid molecules don't repel each other. That's not true, and that's not why liquids separate. Gas molecules attract each other. For real gases, this is in fact true. The molecules are going to feel dispersion forces between them. And so this is really only going to play a role when they get close enough together that they can feel those intermolecular forces. So when they're close to their liquefaction conditions. So that, of course, is not going to answer the question either, because that explains more of liquid behaviors again than gas behaviors. Okay, so the next video we're going to talk about the development of the ideal gas law and what kind of calculations we can do with that to understand the behaviors of gases.